Anyway, enough psychology. Are there any questions from last week's class? No questions? Okay, then I will quickly summarize what I had talked about last week. So, oh, I haven't sent you the reports on that, I'm sorry. I forwarded to Usman. You can send it to the rest of you. So, last time I explained the general idea of space-time symmetries. What are space-time symmetries? Right? I talked about generators of symmetries, right? So like momentum, is a translation, generator of translations, right? Momentum generates translations in space. Angular momentum generates rotations, right? And the total energy, or what you would also call the Hamiltonian, right? This is the generator of time translation. It's the generator of time rotation, right? Because we find that this is the reason that the operator H in quantum mechanics is identified with the time derivative. You can set the fans to your reference. I just turn them down a little bit because it becomes very loud if it is like on feeling wrong. So when you have this association between generators and translations, and generators and the operations that they are responsible for, then it becomes really simple to understand where many of the equations come from. So this is also what I talked about last time. This as an example. If you look at the relativistic energy momentum relationship, okay, so which is E square C square minus plus M square C4 is equal to the total energy squared. And if you replace these by the respective operator versions, right, what you get is C square operator B max square C4 M square equal to operator B square. What you get is what's known as the Klein-Gordon equation. The Klein, so Klein-Gordon. So what you do is for P you replace momentum, or in general the gradient operator. For E you put time derivative, right? if you put these in here, you get dt square plus del square uh, plus del square is equal to minus n square. Then the factor of c goes away. You can absorb the factor of c in the definition of the point example. And now all of these are operators. Operators act on something. The simplest thing they can act on is some function of space-time. So phi of x mu, right? And so those who took GR last semester know this notation. Mu means we're talking about space-time coordinates. So mu these lowercase Greek alphabets, they go from 0, 1, 2, and so on. So this equation is called the time order equation. It is a relativistically invariant equation, right? So this is the first exercise of your first homework set. Okay? To show that time order equation is invariant under Lorentz transformation. Those of you who took general relativity, you will have an easier time proving this. Those of you who didn't, you might still be very familiar with these aspects. But in any case, I'm going to like ऐसे ही धकेल देंगे हमें मेरे in the deep end of the pool. Well, don't worry, I'll give you some. What do you call that? Life support jacket. Life jacket. Okay? So I'm going to talk about Lorentz transformation. I haven't yet said when this homework is due, right? It's the second part of the second exercise. Okay? Now, strictly speaking, time quantum equation comes near the end of this course. Okay? But so I'm using this equation as a means of reminding you of the various very basic techniques that you need to know. Right? So using Fourier expansion, right? Now everybody here knows what Fourier expansion is. We've all done this Fourier analysis, right? So in Fourier expansion, you have some function of space and time. Maybe you have not done the space-time version of Fourier expansion. Maybe you have only seen the spatial one. But there is not much difference. You write this as an integral over some function. So in Fourier expansion, what happens is for each, so if you have some function which depends on n variables, and you do a Fourier expansion, then in the Fourier series you will have some momentum index, right? Some momentum vector. That momentum vector will have as many components as the number of your dimensions here, right? So if I put this as x mu, right? X0 is t, so on. then I will refer to my momenta as k mu. So k mu will be k0, 1 to 3. Right? So this will become a function of k mu. Right? After this, what comes next? Exponential, right? You basically, so what is the Fourier expansion? It is just a change of basis. Right? These states, they are vectors. Right? So you are writing them in terms of a different basis. Which basis? This is called the momentum basis. So when you write one set of, if you have a vector B, right, and you have some basis states Ti, where I goes from point to whatever is the dimensionality of your space, right? Then how would I write a vector of this form? I would write it as Bi, Ti. Okay, I'm just expanding it in this basis. Now, for those of you who have not seen this notation before, let me introduce to you. This is what Einstein's summation notation. Okay? All of you should have seen it, but in case you have not. And we will be using this, we will be using this, so you should know what it means. Whenever you have two indices that are repeated in any expression, it is understood that you have to sum over those two over that index. So this stands for this expression where the summation is implied. Whenever you have a double index, that means it is summed over. This is just vectors, vector spaces. Okay? This is like class 10 stuff. Now, let's say I have a different, I can have more than one set of basis vectors, right? So I can introduce another set of basis vectors. Let me call it E prime. Again, I will run from 1 to n only, right? So, if I have a vector, I can write it in terms of either this basis, right? Or I can write it in terms of this basis. So now my coefficients will be different, right? So maybe I'll call this W, right? But it's the same vector. Okay? So now these two are equal to each other, right? So I have Pi, Pi. Actually, let me continue using B prime because B tells me that it's associated to the vector is equal to Bi, B prime I, E prime. Okay? This is true. Now, these are two basis vectors, basis sets of basis vectors. And we assume that these basis vectors are orthonormal. Right? Right? Orthonormal means that if I take the inner product of any two EIs and any two E primes, okay? Right? So I don't have to use an orthonormal basis, right? I can use a basis which is not orthonormal, but then I can always take the orthonormal basis and convert it into a by pulling out the norm of each vector and putting it into this coefficient, right? Or what is the first experiment? So when we have this condition, so this tells us that, so since this is a vector space, there will be some linear transformation of this vector space. Okay, so let's so that means that these primes I can write using some matrix lambda, which is a linear transformation. Correct? It's a linear because there are only terms which are linear in. The linear transformation is a matrix multiplication. I am using index notation. So, in that case, this expression can be written as, for those of you who already know all of this and might be feeling a little bit bored, don't mind it. It will just make my life easier if I reduce some of these things. Right? So all I've done is just taken this and substituted it. Okay? So this is E of I, E of J, right? So this doesn't yet tell me, so I can sort of see that this sort of, I can see, right, that if lambda is what is used to go from the basis factor to the new basis, then the inverse or the transpose of lambda will be used to go from the components to the new components. Okay? Because we'll see that in a second. Now we want to get rid of these e's, so what we can do is we can take the inner product of both sides with some vector ek. Okay? So ek, bi, bi. Bi is just a number, right? It's not an operator. So this just becomes bi, eki, and since they are orthonormal, this becomes bi delta ki. This is all on the left hand side, and since I is summed over, right, this gives me dk. Okay, on the right hand side again I am taking ek and putting the dot product here, right, and these are all just numbers. So again b prime I, lambda I j, ek, ej. Okay, these are all variables. So again I get delta kj, b prime I, lambda I j, delta kj. Now you can see, by the way, that we are saving a lot of time and energy with this notation. Here I would have two summation signs, and I would have to write this as sum over I, sum over j, and instead I don't need. So sum over j will tell me that this expression becomes lambda I j, sorry, lambda I k, j will become k, b prime, right? So this is on the right hand side. So on the left hand side, what I have is dk. On the right hand side, I have b prime I, lambda I k, right? So now I'm writing it in this way with lambda after I, after b. The reason is because this index is contracted with the first index of lambda. Okay? So what does this look like? This whole thing looks like taking a row vector, okay, and multiplying it by a matrix, right? So if you took some vector b, right, took the transpose of that vector, so it becomes a row vector. Then you have some matrix A. How would you? This is how you would multiply these two, right? So here, if you think of this as a row vector, this is a matrix. That's what I'm thinking. You can also write this as lambda transpose Ki B prime I. Okay? So transpose just means I'm switching the indices, that's all. So if I write lambda transpose, then, right? So lambda transpose AB is equal to lambda BA, right? So the one thing you might be unfamiliar with is the up and down indices. Let me clarify that notation in a little bit more detail, a little bit more carefully. Here, when I have written this, lambda is a two-index object. One index is low, another index is high. In this case, the first index is low. So imagine that there are slots here. There is a slot 1, 2, two lower slots and two upper slots. So I can put indices in these slots. So here I have put one index in the lower slot, in the first lower slot, and the second index in the upper second slot. Basically, the way you travel in sleeper buses. Okay? Up, upper, lower, left, right. So that is why here you can see this slot is empty, right? So that's why I put a little bit of space here. So I space. I could also have, if I take the transpose, what will I get? J comes here, so I write it here. I comes here, so I write it. Okay? If you find this up and down confusing, there's a very simple solution. Just take all the indices and put them down. Okay? There is a reason why we put these indices up and down, but if you cannot handle it, if you think that your life is complicated enough already, then you can put them both down. Okay? So what we see is that if the vector transforms, the basis vector transforms according to some matrix lambda. So when I want to write the matrix, I will put this tilde underneath, okay? So this is the matrix and these are the components of it. And when this happens, the components, how do they transform? They transform according to the transpose of this matrix. Right? Anyway, this is all linear, elementary linear algebra. Okay? So technically all of you should be like experts in this. But the reason I am doing it is because of the notation. So another thing that you might be wondering is why the hell is he using these cat vectors? Right? So that you would have known if you had read in the first class. So I'm using this notation. This doesn't mean that it's a quantum vector, it just means it's a vector. It doesn't say anything about it being a quantum state or a classical state. Any vector I can write in this way. Now, question? Question? So now, what does all this have to do with the Fourier transformation? Fourier transformation is simply a transformation from one basis to another basis. So, in the first basis, I have phi t comma x. Okay? The difference is that these are all finite dimensional vector spaces. Right? N is a finite index. Now I'm calling this a vector, right? This phi. Why am I calling it a vector? If I have a vector, the vector must have some index, no? Some index which allows me to select which component I'm talking about, right? Right? What would be the index here? Huh? The index would just be the space-time coordinates. Right? So you have some region of space-time. Right? With each point to associate some value of phi. So it becomes a vector. So the index is simply the point at which phi is defined. But now, what is it? There is a difference between these indices and these indices, right? These indices are discrete. They go as 1, 2, 3. These indices are continuous, right? So when you have a continuous index, what is the dimensionality of your vector space? It's infinite. So don't let that scare you. Okay? Infinite dimensional vector spaces are nothing to be scared of. So this is one vector, right? What we are going to do is we are going to write it in terms of a second vector. Now this vector will have its own indices, right? Those indices are k0, k bar. Okay? Something I can call it anything I want. I am calling it k. Okay? But these indices, they take values in the same vector space as this, right? If space-time is R31, then this momentum space is also R31, right? So even though we are using different labels and we are calling it different names, this is also the same vector space as this, same kind of vector space. Anyways, so we are doing this transformation from here to here. In doing this transformation, there must be some lambda, something that transforms this to this. This lambda must have one index which corresponds to the new vector and one index which corresponds to the old vector. Right? So this lambda will be something which depends on both p and x, and it also depends on the momentum label. Right? So this is the matrix. Basically, you can think of this as an infinite dimensional. If you want, I can write this as phi I, where I means p comma x. This I can write as phi prime I, where now I means the momentum vector 4 vector, and lambda I can write as ij, where I again means space time, and lambda means, so I'll just write as x cube and k. Okay? So when I'm writing down an expression for a Fourier integral, let me write that expression. Okay? This is equal to some integral. The integral will d3k dk naught, so as you just write as that as d4k times exponential e to the I k mu x mu, I'll explain this in a second, times phi of k mu. Okay. Now once you understand that these are vectors and what we're doing is a rotation of my basis, then it also becomes easy to see that this integral, right? This integral looks very complicated, right? But this is nothing but a sum. So if this was a discrete label, if momentum was a discrete label, this would be just a sum over ki, right? K0y, kxi, k1, k, so on. You would just have sums, 4 sums over the field. But when you go from discrete to continuous, right? What happens? Now this becomes an integral. So if you have sum over I, right? This becomes integral over some dxi or just di. So this becomes sum over x. This becomes integral over dx. So where xi, right? So sum over xi. So you're summing something over some points in space x. So again, this notation can get confusing. So best to just leave everything out in this way. Sum becomes an integral, right? And when sum becomes an integral, in that case you also need to put some factor here, which looks like something 2 pi to the power 3 halves. And then there is actually another factor here, which is root 2. So again, I'll talk about that factor, why that factor is here. Okay. But first, what is this k mu x mu thing here? So again, let me go back to the Fourier transform. In ordinary space, you have some function x. How do you write this Fourier transform? You write it as something f k e to the I kx dk. Right? If you have something which is a function of 3 variables, you would write the Fourier transform as 1 over 2 pi, 3 halves, 1 factor for each dimension. F becomes a function of 3 different momenta. This becomes e to the I kx times x, e to the I ky times y, e to the I kz times z. Okay? And then you have an integral over kx, ky, kz. Right? Now this expression can also be written as e to the I. You can put them all in one exponential. Right? And in which case this becomes e to the I k dot x. Right? So this will then be written as f of x into 1 over 2 pi 3 by 2 integral of x dot k e to the I k dot x. Then I have integral over 3t of the k's. So I would write it as d cube k. I can also write it as d k bar, d vector k. So these two things will mean the same. Whether I write this or this or dkh, right? It's all the same thing. So this is my expression for the Fourier transform of a function, right? When I am going to space-time, I am including one extra dimension. So if I am including one extra dimension, see, this x here, there is nothing in this expression which tells me whether this x is 3-dimensional or 2-dimensional or 1-dimensional. Because I have replaced everything with a dot product. So if I have x is 4-dimensional, doesn't matter. All I need to do is just take the dot product in 4 dimensions. Right? The dot product in any number of dimensions I can take. I know how to take, right? It will be k0, x0, k1, x1, some. Right? Wrong. Well, not wrong, but it applies only when we're talking about space. When you mix space and time, right? So then what will happen is you will have x mu, so that is x0 x, and k mu, that is k0 k. Okay? So when you take the dot product of these two quantities, right, you will notice that in this expression, here I am writing mu with an upper index, here I have written mu in the k with a lower index. What the hell is going on there? The reason is these indices, so now this is no longer a spatial vector, it's a space-time vector. And it is because we are working with space-time that we need this up and down. Because there is a difference between this vector and this vector. The difference is the fact that the sign of the first component changes. So when I take this vector, lower the index, it's exactly the same thing, but only the sign of the first component has changed. That's the sign of the time component. So now when I take this k mu x mu, this expression, right? It's not just a simple k1 x1 k2 x2. It is, where is it? Okay. That's why different color chalk is helpful in this. K mu x mu becomes minus k0 x0 plus k dot. Alright. So this is the Fourier transform of this quantity. And here I forgot to put a filter because this is a different function. The form of that function is different. Okay? So up till this point, apart from the complication with these indices and these minus signs, I have not told you anything that is new. I have talked about vector spaces, I have talked about transformation of vector spaces, I have talked about Fourier transform. All of this is old material, right? All I am doing is I am just packaging it in a different way. I am packaging it in a which will make the relativistic content of the expression clear. Okay, we have not come to relativity proper yet. I am explaining the notation and how to package things in relativistic. And when you are first reading about relativistic physics, or when you are first learning field theory, one of the things that can be an obstacle, often is an obstacle, is precisely this packaging. You know what a Fourier transform is. You know what a vector space is. You know what a transformation of a vector space is. But when you look at this expression in a book like, let's say, if you field theory, Besson and Schroeder or something like that, don't know what to make of it, right? Because indices are there, there's this factor here. This factor will be explained later, okay? For now, in your notebooks, you can put a little question mark around it. So that way you know that, okay, it will be explained later. And if it's not explained later, you can always come back and say, explain it. Alright? This is fine? Are there any questions? So this is the Fourier expansion. Now what does all of this have to do with this Klein-Gordon equation? Right, I was talking about the Klein-Gordon equation in the beginning. So you know what Fourier expansion allows you to do now? It allows you to solve linear differential equations. Linear, it's not the non-linear ones. I mean, you can use a Fourier expansion, but you won't get a simpler. So let's write down this Klein-Gordon equation again. Okay? dt square plus del square minus x square phi xt equal to 0. This is my equation. For the time being, I will set L to 0. Okay? So we are just looking at the massless equation. So with m is equal to 0, this equation takes the form d square phi by dt square is equal to del square phi. Okay? And in order to make dimensions correct, so this is derivative with respect to space. So what is the dimension of a spatial coordinate? L. What is the dimension of the derivative with respect to a spatial coordinate? L inverse. So phi also has, everything has dimension, okay? Or it doesn't, but you should always be very careful. So phi has some dimension d, okay? But that is the same on both sides, so it's fine. We have del square has dimension 1 by del square, right? This has dimension 1 by t square. They're not the same. This is t, that's L. So in order to make the dimensions the same, I should put something here. Right? This quantity should have dimension of L square by t square. Oh, sorry. Yeah, L square by t square. So then the total dimensionality becomes t square by L square 1 by t square equal to 1 by. What is this quantity C? The speed of the speed of a wave. This is the wave equation. Right? This is the equation for if you take a homogeneous isotropic medium, okay, and you ask that if I displace one element of the medium right in the middle, what will happen? It will go back and forth, right? And release it, a wave will be generated. Right? That wave will propagate through the middle with some speed. That speed is called the speed of sound. Right? So this is the speed of those waves. Right? So when you are in space-time, in this case, light, right, is propagating. You can think of this as speed of sound of the vacuum. Anyways, so now we have this expression. Let's write that again. 1 by c square dt square phi is equal to dt square. Right? Now, the Fourier expression makes this very easy to solve. It becomes just a two-line answer. So, what do I do? The first thing is this phi, instead of phi, I substitute this expression. Okay? When I substitute this expression, on the right side I am taking the time derivative. On the left side I am taking the time derivative, on the right side I take the spatial derivative. Right? And twice. Now what happens when you take the spatial or time derivative of this Fourier integral? So if you look at this whole expression, if I write it again, 1 by 2 pi r 3 by 2 integral d I is k mu x mu. Let me write down what you get. You get minus k0 x0 plus k dot x. Okay? Keeping in mind that k mu with index raised, keeping in mind this is how you take dot products in space-time. And then multiplied by some function of k only, right? So I am taking the derivative of this whole expression, and this derivative will seem like, again, like taking the derivative of this whole expression. But if you look at this expression, this doesn't depend on. So let's say I'm taking the derivative of this expression with respect to time. This doesn't depend on time. This doesn't depend on time. I have one single exponential factor which depends on time. X0 is what? T. Huh? So when I take the derivative of, and then I can, since the derivative is not in the integral, I can just take the derivative. So what do I get? I just get d by dt e to the I minus I k naught t. This is the only thing I have to take the derivative. What will I get? I will get minus I k naught e to the minus I k naught. Right? Times. So that's it. So if I take the derivative of this whole expression with respect to t, what do I get? I get exactly the same expression times minus I k naught. That's it. Right? So I get minus I k naught times this whole expression. What if I take the second derivative of the same expression? I get two factors of this. So I get minus k naught square. So in this expression, I get here minus k naught, minus of k naught square. Minus I square gives me minus k naught square times this whole expression, okay, this whole Fourier expansion, you have to put it there. This is equal to the second spatial derivative. The second spatial derivative now again, if you take the derivative with respect to x, you will get kx, you will get ikx or iky or ikz, right? If you take the second derivative, you will get minus kx square or minus k naught square minus kz. Here, okay, so here from going from here to here, for simplicity, I have restricted myself to one spatial derivative. So here I will get minus kx squared times this whole same Fourier expansion on both sides, no? Right? So this I can cancel out because it's the same. It's the same thing, right? It's the function phi of it. So this tells me that k naught and kx are not independent. There is a relationship between these two. What is that relationship? It's kx squared minus k naught squared is equal to 0. Okay? So this is for one dimension. The case for 3 dimensions is simple. Why? Because del square can be written as del x squared plus del y squared plus del z squared. As long as we are working in Cartesian coordinates. If you go to polar coordinates, life becomes a little bit more complicated. So now you just have to take del x square will give me, so del square phi, del x square will give me minus kx squared, then del y square will give me minus ky squared, del x square will give me minus kz squared. All of this times phi. This whole expression is nothing but minus k square, k being the amplitude of that vector, right? Because kx square, ky square, kz square. So in that case, this expression becomes k amplitude squared or just k square minus 1 by c square k naught squared, right? What is this k? Physically, what does this spatial k, right? What does it represent physically? It represents the momentum, right? You would say that the momentum of this, of this state, right? It describes the state. I have not said whether it's a quantum state or classical state is just a state. The momentum of this state is E equal to h by m. Actually, it is not. If I'm going to do this, then yes, it's a quantum state. So this k square is momentum squared divided by h bar squared. Okay? So this becomes 1 by h bar square, e square by h bar square. On the right side, I get 1 by c squared, k naught squared. Okay? What is the interpretation of k naught? This might be unfamiliar to those who relativity. In relativity, this k vector, k mu, it becomes what is called a 4 vector. So this I will talk about more on. So this 4 vector, it has these components. The first component is E by C, that corresponds to the energy of the particle. So this tells me this is equal to E square by so there's some factor of C is extra, okay? So I'll just assume that everything comes out. And wait, is there a factor of C extra? So this becomes E square by C4, is that?
Yeah, it's fine. It is E by C only. K0. K0 is E by C only. K0 is E by C only.
I know K0 is E by C. I was looking at the dimensionality of this expression, just making sure that this is C square and not something. Anyways, when in doubt, set everything to 1. Okay? You can always take your constants and set them to 1. So you are left with this expression P square is equal to E square. Right? So you actually get P square is equal to P square C square, right? So that's why what is this? This tells you that the particle is what? It's the massless, right? So each one of these waves, right? This is a single wave, right? Each one of these waves, this is a basis vector now, right? You remember? These are the components in one basis and the component in another basis. So whatever is here, this is the basis vector, right? These are the basis states. So each basis state is a wave. Okay? This is a plane wave. That's what this e to the I kx is. It's a plane wave. And this is what? Omega t. Right? So your basis vectors are plane waves. Right? And because they describe massless particles, omega t is related to the momentum by this relationship. And E is equal to h bar omega, Planck's relationship. Right? So you can also write this as E is equal to Pc, which is the same as h bar omega is equal to P is equal to h bar k. C. So h bar and you get omega is equal to kc. Right? Does this make sense? Omega is equal to kc. Omega is the omega is equal to 2 pi f. Right? K is equal to 2 pi by lambda. Right? So this tells me 2 pi f is equal to 2 pi by lambda times c. This tells me f times lambda is equal to c. This is what we expect now. Velocity of the wave is equal to the wavelength times the frequency. Okay? So tomorrow I'll start with Lorentz transformation. Okay? So these first two lectures were intended to give you an idea of what we will be doing. Alright? Are there any questions? This is questions. You're being on camera.
Why do we normally use Schrodinger equation instead of?
Huh?
Why do we normally use Schrodinger equation instead of?
So the question that Asman is asking, why do we not use the Schrodinger equation instead of this equation? Okay. Nobody knows the answer? Huh? It's not Lorentz invariant.
Yeah, I was asking why don't we normally use this equation instead of Schrodinger equation?
Oh, sorry. His question was, why don't we normally use this equation? What's the answer? Huh? No, not necessarily. I mean, okay, well, sure, maybe, but in our normal experience, do we need to use relativistic quantities?
Can.
No.
No. But
No,
it will get
Manas.
cancelled.
We need to use, huh?
But it's not going to affect anything. No, I was saying that we can, but it's not going to affect anything.
Don't worry, I get that part.
Okay, sure.
We are in the Schrodinger equation describes non-relativistic phenomena, right? So when you take the Klein-Gordon equation with mass, massive Klein-Gordon equation. So if you have a non-relativistic phenomena, then it has to have some mass. There should be a mass parameter, right? Things become massless when they are relativistic. So you have the massless Klein-Gordon equation. Does it reduce to the Schrodinger equation? I'm not sure. Not sure. But anyway, we don't use it because we are in a non-relativistic world now, at low energies. Anything else? Alright, we'll see you all tomorrow morning. Everybody has the first exercise, I hope. Still.